So let's continue. I will first remind you of some key ideas related to the quantum mechanics of tunneling. Now, the first thing to do is that we need a description of something that is traveling. In atomic problems, in particle in a box, harmonic oscillator, rotor, hydrogen atom, molecules, bonding, we always look for so-called stationary states, the energy eigenstate of the Hamiltonian. That will be the atomic orbitals, molecular orbitals, etc. Those are not traveling, okay? So if you want something traveling, we need to think about something else, like plane waves. I know the last term, you have learned about this traveling wave and its normalization. But here I just would point out there is really something extra in relation to what we have done so far about the stationary states. So we need something traveling. So take the example about traveling freely. Freely means the potential energy is zero, so you only have the kinetic energy part in your Hamiltonian. So the energy becomes p squared over 2m, therefore it is h bar squared k squared over 2m, okay? You can define something like a frequency, which is E over h bar. And then you have this typical plane waves. And you know from this exponential, you have to work hard, you have to run with the, as time proceeds, if you want to keep yourself at the top, then you have to run with it, okay? And then you are traveling together with the wave. So it is traveling to the right-hand side as time evolves. And if you have this minus ikx, then it's traveling to the left. So it seems to be easy to have something that can travel, all right? But there are technical issues. For example, a question is how to normalize something like this, eik dot r. If you multiply it into the psi star and then it is a constant, it is 1, you integrate it over all from negative x to negative infinity to plus infinity, that diverges, right? Okay, so normalizing this is actually an issue. Deeper, it is an issue related to this allowed energy being continuous. Okay, if you don't have anything bounding the particle, it is a continuous spectrum. I know that you have this Dirac delta function last term to normalize this kind of funny wave function with the plane wave. Okay, so there are ways out. Okay, one way you learned is to invoke the Dirac delta function. Now, to me, I would say that this is changing the normalization definition. Well, because this is a 1 over k dimension, right? Okay, so you are not normalizing something to 1. Okay, and if you want that, well, that's fine. You stick to it. And there is some basic idea behind it that comes from Fourier analysis. So this is one way out. Another way out is to do things in a more complicated way, but doable, is not to consider plane waves, but to consider a linear combination of plane waves forming, using different k's, stack them up to form a wave packet. Okay, that is to say, when you consider the tunneling problem, you have something coming in, you have a wave packet representing the electron or some particles coming in, and then see what happens. That is a very good way to do it. Formal, no problem about normalization because wave packet can always be normalized. And then you can actually see what happens as the wave packet hits the barrier. A very interesting thing, okay? But the calculation will be harder. A third way to do that is something called the box normalization, a rather clever idea. The idea is to use a finite space, but rather big one, so as to mimic, to model an infinite space. The idea is this is a one-dimensional analogy. I have a long wire, L in length, but I connect the two ends together so it's like a circle. Think about yourself running on the track that is, 3 kilometers wide, okay? And you're running it, or 500 kilometers wide, like CERN, okay? So now, as you run, basically you sense that you're running along a straight line when the circle is very big, okay? So that is the idea. But in this case, we have this clockwise circling and anti-clockwise circling direction that could be represented by this EIKX and E minus IKX waves, okay? If you do that, actually you have a finite system, length L, therefore you can formally normalize such a plane wave looking wave function, all right? So normalization becomes okay. For those who have worked on this particular normalization method, there's a price to pay. The price to pay is that you have to impose one further boundary condition. For the reason that if you start here, call it X, you run L again, you call it X plus L, but you are at the same place. So this is an additional so-called periodic boundary condition. Okay, the consequence is that your K, allowed K, will be discretized again, just like you have a finite size system that confined the particle. So, it's not that simple. That's the message I want to convey. When you have something traveling, actually there's some issue, a rather basic issue about normalization. I will not go through all this technically in detail, okay? You might have known one or two of this. The second basic idea is probability current density. I know that you have this formula before, right? This is the probability current density. Then you have this prefactor. The I is important here, so h bar over 2mi. And then you have these two operations and subtract them against each other. So this is the definition of probability current density. So just like E and M, this current density will go with the probability density with a continuity equation, okay? Then if you work it out in 3D, then it is this definition. The gradient is a vector, thereby this is a vector, okay? This is a flux, basically, okay? Something over meter square per time. Usually in tunneling problem, our standard simplest case is one-dimensional. So I just want to remind you that in 1D, this becomes that, okay? It is still a vector, pick up I, one direction. So the 1D version of this current density becomes the derivatives, okay? And then it picks up one direction. I call this Jx, okay? Then something started to become more interesting. We just talked about this plane wave looking thing. You may wonder why I need the partial derivative. Actually, what I mean is that this can be x and t at the time. Okay, so still you still have another variable. So now we talk about the plane wave, and we point out that there are issues about normalization. But the nice thing that turns out is that no matter how you do it, the answer will be the same, okay? So I don't care about how you normalize it. I just write down an amplitude A out there, okay? So let's look at this. When we have such a form, the question is, what is the probability current density? Okay, now this is an interesting situation because traveling to the right, so incident, okay? So what is the probability current density? Well, we plug formula, we plug this into all these places and do the derivative, all right? Then you will see the first term, the second term. For each derivative, you will bring out ik, okay? So I have this ik, but this star helps, okay? So I have minus ik when I take the complex conjugate, thereby I have minus ik. Now look at some magical thing happen. The definition has a minus, and then there is a minus. So this term add to this term. So I have 2i, okay? And I have an I that cancels, and I have a rather simple answer. H bar k over m, the magnitude square, okay? So this is the key result. Summary. Next time, when you see a wave of this form, the J is this form. That's it, okay? Now, if you think about the physics, it also makes sense. You can almost obtain this form without doing the plugging in the formula. If you realize that this is the momentum, this is freely traveling, okay? Then momentum divided by m is the velocity, okay, the speed. And a square is the amplitude, psi square is the probability density of the wave. So this is how strong the wave is. This is how fast the wave is traveling. So that gives you the probability current density. Makes sense, right? Probability density traveling with this speed give you that. Okay, so that is the meaning. All right. So summary. Next time when you see this, J is that. Done. All right. Now, more interestingly, you can think about the opposite traveling one. Okay, minus ikx, and then you can almost immediately by argument, this is the current density. Okay. Now, what if I have this linear combination? Okay. Now, for those students who haven't done this, I think it is one of the must-do exercise. Plug this into the definition. So the definition is here. Okay. Now, first appreciate this thing will have two terms. So that's why I have two terms here. This thing, after you do the derivative, two terms. This thing, two terms. Do the derivative, another two terms. Okay. So each one of this is 4 terms. You multiply this thing will be 4 terms. Another 4 terms. Okay. Understand? This bracket has 8 terms. Somehow, after you cancel things, the current density is this. Okay. Now, I haven't shown explicitly that to you, but this is a must-try exercise. Summary. Next time when you see this, the current density is just, think about this is one wave going to the right. So it is traveling to the right plus I with the speed in this probability density. Okay. And then there is another term going to the left, v minus ikx. So it's traveling in minus I. This is the speed. This is the probability density. Okay. Now, I would say it's not trivial. Maybe it's trivial to you. But if you understand this whole trunk has 8 terms, at the end, there are only 2 terms. There's something worth trying. So take home message. When you do tunneling problem, you like to say, the left-hand side has an incident and a refracted wave, thereby it's like that. Okay, so next time you see that immediately in your mind, without doing anything anymore, this is the current probability current density. Okay, pretty nice. Now, for those who like to plug formula and play with things, how about this? Particle in a box, ground state, it evolved with time like this. Okay, so plug it into the J formula. What is it? Okay, if you now 5 seconds, 5, 4, 3, 2, 1. If you know the answer is J equals 0, good for you. Okay, but if you don't, try it and you get 0. And then how about this? Linear combination of a particle in a box ground state and the first excited state. Okay, plug it in. Again, you have many terms, 8 terms in the bracket. See whether you can cancel things off. Worth trying. But even more interesting, how about this? I have a wave function. This version is 3D. This version is 1D. I have a wave function. It is complex in general. Therefore, I can always write it as a magnitude times the EI phase, delta of R, okay? What if I have a phase that is spatially dependent? It depends on where is it in space, okay? Now plug it into the definition of J, okay? I think you will pick up some term definitely that is the gradient of the phase. Okay, it is very useful. Okay, for those students who are crazy about quantum mechanics, I'm not. If you are one of them, try this. Okay, you will pick up a current density that is proportional to the gradient of the phase of a wave function. Later on, if you study more condensed matter physics, there is one example of this particular scenario in superconductors. If you have two different superconductors next to each other, forming so-called Josephson junction, there is a current that is actually this type of current. So that is just a reminder, part A, okay? So now part B. I would like to remind you of this typical and the simplest quantum barrier problem. So it is a square barrier. It's a flat barrier, okay? There's no change in the potential. If you have a triangle, go like this, go drop down, it is more complicated. So it's the simplest thing. So region 1, 2, 3, all right? I know many of you have done this. So I just want to remind you the procedure. We are interested in an incident energy that is below the barrier. So tunneling, hopefully something happened here, okay? Classically, it will bounce back definitely, 100% chance you will not see anything on region 3, okay? So that is the range we are interested in. But at the end, the result can be translated into incident energy above the barrier. So we write down wave function in region 1, 2, 3, okay? So region 1, you have an incident and a reflected one, thereby we have our standard thing. Nice, okay? Just to remind you, the K is given by the dispersion relation, the energy K relationship. It is 0 potential here, thereby it is like this, free particle. Therefore, the K is hidden. The energy is hidden under K. So when you see K, that represents the incident energy, okay? The region 3, we have the transmitted part. Formally, you have the part from the infinity plus infinity side, but exercising boundary condition, You throw that term out because you're doing tunneling, okay? So you have this, and then in the region 2, this barrier thing, you have this E minus kappa x and plus kappa x. It's not I something for the reason that E is less than U, okay? And the kappa represent the energy deficiency. How far E is from U, okay? So it is U minus E square root, okay? So therefore, kappa contains the information, not only the incident energy, but also the information about the barrier height, the U. So it is actually the energy deficiency. Okay? Then the picture is like that. And suddenly we can write down a lot of things, right? We just know that when we see this, the current density is that. We have an incident part and a reflected part, as we can identify it from the wave function, okay? How about the transmitted part? This term, nice, we already did that, okay? So we know the transmitted, the current density in region 3 and in region 1, all right? Now they are useful because we must go through this J discussion in order to define what we want to do. We want to get something called the transmission coefficient and the reflection coefficient. They are defined in terms of the current density, okay? So what is that we want to get? Here is the definition. We want to get the reflection coefficient R, defined it as the reflected current density, actually it's probability current density, upon the incident probability current density, okay? Therefore, it means take this term divided by this term, okay? Then we are done. It so happens that the prefactor canceled out, and then we are looking for B over A. That is our target. But more importantly, we want to get transmission coefficient, which is defined as the transmitted probability current density over the incident one. So from the formula, we know that it is the transmitted current density divided by the incident one. In this particular problem, now pay attention, only for this particular problem, with these two sides being U equals 0 on both sides, the prefactor cancels. And then we are looking for F over A. All right? Now, let me stress it one more time. This is the formal definition of R and T. Okay? Now, if you have a situation like this, yes, clever, right, Mr. Lau, this is exactly that EM problem, okay? Look at the chat, okay? Good remark there. Related to optics or EM wave, yeah. So now, if you don't have the situation where the right and the left-hand side are the same potential energy function, but say the right side is slightly lower, then be careful. The transmission coefficient will not be that simple, but it's not complicated. All you need to do is to follow the definition, okay? But on the third region, you will have to pick up the velocity, the momentum, okay? That is the K. So you need the K in the third region over the K in the first region, okay? So the point is that I want to remind you, it is the concept of J that is closely related to tunneling problem. So now, how to solve for F over A, B over A? Easy. Match boundary conditions at the two interface, 0 and the left-hand side and the right-hand side of the barrier, okay? And L. L is the width of the barrier, all right? Now, in the past, you may be focusing on wave function continuous and the derivative continuous. But actually more physically, it is the J that is continuous. It is the current probability current density that is continuous, just like your E and M, okay? But luckily, in this simple case, when you exercise the slope of wave function being continuous, you are automatically guaranteeing J is also continuous, okay? But it is actually more physical to go this way than the other way, okay? Now, after you do that, you have a set of equations, simultaneous equations, solve, okay? And I just copy out the result. The result is the transmission as a function of the incident energy is given by this, okay? I just want to remind you several things. The incident energy is hidden in K. The kappa has U in it, the barrier. It contains the deficiency, the deficient in energy to pass through it on top, okay? And L is the width. Therefore, this transmission formally is a function of the incident energy and also the shape or the parameters of the barrier, height and width, naturally, right? And it comes with a rather unusual form, but I know some students already did the E and M course, you must have seen this, okay? So it is the same denominator. The next form, I just explicitly write it out. So you see E, you see U minus E, and you see L, okay? Similarly, you can solve for the reflectance, reflection coefficient, and then you can check that this plus that happens to be 1. Of course, you don't have absorption. You don't have loss, energy loss mechanism. If you have, you don't have this equal sign. Okay. Now it's more important to have some physical sense on tunneling. In particular, look at this singe function. Definition is this. For our problem, tunneling, we usually have thick barrier and large energy deficiency. Okay, that is to say, capital L is usually big, thereby you don't need to worry this term, you have this term. But this term unfortunately happened in the denominator, and then the transmission, this is the punchline for experimentalists and all students, is exponentially minus, okay? With the width of the barrier and the square root of the energy deficient. Okay, that is the amount of energy insufficient to surmount the barrier, and then this is the width, okay? The exponential is important because it means it is very sensitively depending on L and how much energy you don't have. Okay, so that is the most important form instead of this form. So it means the following. If you let the barrier width decrease by a little bit, move it slightly, T can increase by much, okay? Or you make it bigger, it will drop by much. Or else, if you decrease the barrier U by a little bit, the tunneling probability, the T, transmission, will increase by much, very sensitive, exponentially. So this is the dominating behavior, okay? Although there are other behavior in the prefactor, but the exponential one is the most important physics. Then look at what does this answer means, okay? In plotting, I'm using the complete form, the total form, okay? So tunneling means the following scenario. Classically, if the energy of incidence is below the barrier, it is zero chance to get through to the other side. So the curve will be T is 0 all the way up to E equals U, okay? And it will jump to 1 when E is greater than U. It's a step function classical mechanics, okay? Now, quantum mechanics, tunneling is defined by the following. U is less, E is less than U, so I only focus on this range, okay? And then I'm using some particular parameters there about the barrier and the width, okay? It is small, but non-zero. So it has something like this. It's just a tail, but not big, okay? But it's already very different. And this is called tunneling. But there are also quantum effects even for the energy over the top of the barrier. We can modify this end result by taking kappa into ik prime. Because when you go up, the decaying, growing become sinusoidal, becomes exponential, things like that, okay? So we can replace the formula by ik prime, and then we get, we don't need to redo the algebra. Of course, you can redo it without knowing that, okay? So in this figure, I supplement in the other region. We talk about this region, okay? But for E greater than U, you also have some quantum effect. You see this oscillatory thing, okay? So you have region that is even. E is greater than the barrier, the transmission is not 1, all right? Now this should be contrast with the classical mechanics situation. You have a step function, okay? Only when the energy is well above the barrier, the transmission is 1, therefore it goes with the classical behavior. I know that some of you have learned E&M, so I take a page from Griffin's exercise, the chapter that is a problem, and then it asks you to solve the following problem. The fish is in water, there is a glass, you are in the, what do you call it? Aquatorium, 水族館啊, okay? And then you are seeing that, and then so this is the standard case. N1, N2, N3 referring to the reflective index, and you are asked to prove 1 over transmission is something like that, okay? You flip it, it is, this sign is in the bottom, okay? It is signed because it is like above the barrier. Now for those who like algebra, try this, okay? Step function, double well, triple well, a lot of wells that will become a solid problem at the end. But what if you don't have step barriers, but something like this, don't worry, you cut it into many rectangular one and then combine the result, okay? So there are things to do. So let's get back to the motivated problem, alpha particle decay, okay? So again, we have this, a alpha particle trapped inside the nucleus, okay? It may come out through tunneling. We already motivated, I used the same page here, just to remind you. So we have a barrier to tunnel through, okay? Depending on the energy trapped here, it will be very sensitive. The transmission will be very sensitive to the kinetic energy. So the situation is depicted as follows, okay? The alpha particle keep on trying, okay? So very often it's bounce back to the other side, try to go out and then bounce back, bounce back, bounce back. Occasionally it will come out, okay? So what is there some number to quantify that? So here I just use very typical numbers, give you a rough estimate. I'm taking a nucleus, you said it's 90, therefore there will be more than 90 neutrons in it. So it will be a big kind of heavy nucleus. The kinetic energy of the alpha particle is 6 MeV, rather typical. And then the radius of the nucleus, again, some femtometer, very typical ones. And then I try to estimate the barrier that it has to go through and then just plug some numbers in, okay? Now, typically, let me tell you the answer. When you do this, basically, you will get a rather depressingly small number, 10 to the minus 29. That is the transmission probability. What does it mean? It means that if the alpha particle takes one attempt, okay, it has the probability of 10 to the minus 29 to come out, okay? So you may wonder, why on earth we can still see alpha decay, okay? And the following spirit is highly educational, okay, students? The spirit is keep on trying. 勤有功, 錢有功, okay? If one trial is very difficult to come out, you just keep on trying, okay? Then I want to estimate something for you. The radius is something like 7 to 8 femtometer. So the diameter will be doubling it. So 15 femtometer. From the kinetic energy, we can estimate roughly what is the speed of the alpha particle moving inside the nucleus. So hey, let's take it 10% of speed of light. You can take another number, doesn't matter, okay? The point is still there. So per second, the alpha particle is travel back and forth. The nucleus 10 to the 21 times. So it is really trying very hard. Every second, it is making 10 to the 21 attempts. And per attempt, a tiny probability to come out. Thereby, when you multiply the two things together, you still get a probability for decay per second that you can see experimentally. And that is the fact that alpha particle can come out, okay? But then it also explains the phenomena. Why? The kinetic energy is changed by a little bit, then the lifetime can be much shorter, okay? The kinetic energy is a little bit lower, then the lifetime is much longer because of tunneling phenomena, the exponential sensitivity. Okay, so that is one traditional application in the early days of quantum mechanics to explain tunneling. And one of the people is this guy, a Russian, very famous physicist. He also wrote many popular physics books, okay, in the early days, popularizing physics. So other applications that I would like to mention below. Very famous one nowadays become a standard apparatus, STM, scanning tunneling microscope. This is actually a small size stuff, a tabletop stuff, okay? So this is a the apparatus, the idea is as follows. You have a sample. The sample should be conducting. Now that is a problem. And then you have a tip. Okay. So it's like the tip of the pen here. Okay. Of course, we are talking about a tube that we believe at the end is one atom. Okay. And then you have a sample. Of course, the sample is just that tiny. Maybe it is the sample that you want to make use of it as a solar cell, and you want to see what is the surface. How does the surface, the atom sitting on the surface behave? Okay, that's the problem. So now I blow it up like this. Okay, this is my sample. Okay, so the idea is the following. I try to move my tube. Don't touch the sample, but keep the tube something like just 1 to 2 angstrom away from it. Okay, now it is easier to say than done. Okay, but you don't touch it, you control it. Okay, in that way, there will be electron tunneling through, either from the sample to the tube or from the tip to the sample when you apply a circuit, a bias. Okay, so you can detect a current. Then the trick is as follows. When you move, you scan the tube around, you try to keep the current signal a constant. Okay, so let me use my head as the atom. So I'm doing this. Okay, now if I move the tube so far, the current will drop. I know that is not right. I need some circuit feedback to move the tube back close to me. And then it keeps on doing it, okay? So keep the currents constant. It will, if you record the movement of the tube, you are tracing atom by atom that lives on the surface of a material. Okay, do you understand the idea? Okay, now, it is very sensitive because of the exponential behavior. Okay, so that's the idea. And that once this guy a Nobel Prize is very fast. 3 years, they got the Nobel Prize because at that time, many labs in the world already got this apparatus and they are using it happily. Okay, so it works, that's the point. And this is one of the early Nobel Prizes that were awarded for invention of a new apparatus. So this is what I just told you. You keep the current, you try to keep the current constant, the constant current mode. You can map out these are meant to be the very first picture of atoms. Although atoms have been discussed philosophically by the Greeks 2,500 years ago. Only in the 1980s, we see pictures of atoms. Nowadays, it has become routine, okay? A byproduct, rather accidental, is that this STM tube, I think some experimentalists may have made some mistake touching the surface, but when they touch the surface, they found that sometimes the tube is able to pick up some atom and move the atom to somewhere else and put it down. So now it becomes another tool. So here is a picture of putting some extra xenon atoms on the surface and then use the tube to place the atom at will so that at the end IBM was painted by the atoms on the surface, okay? So obviously it's done by IBM. Of course, one can write Chinese, okay? But it's written by Japanese, I think, this one, okay? There are more applications of tunneling in the early days. Again, we heard about work function, right? Photoelectric effect. We heard about work function, and there are other ways to get electrons out of a metal. That is very important in the early days of quantum mechanics development as well, because there are many experiments that use cathode ray tube. You have two cathode anodes, and then you apply voltage, electron will fly out from one end to the other, okay? For many years, computer monitor, TV sets are designed as a cathode ray tube with the electron hitting some fluorescence stuff on the screen. Therefore, on this end, you can enjoy TV shows. So what is this idea behind it? It's called field emission. You apply a field, electron can come out from a metal, okay? So in a metal, you can think about that the electrons are trapped inside, that's why they are not coming out. The work function is the minimum energy for them to come out, so there's a barrier of the work function, okay? So you can think about this as a potential energy trapping the electrons inside the metal, okay? Now, if you apply an external field, the idea is that a constant uniform E field will give a linear potential energy because gradient V is E, okay? So when you apply a field, basically you are bending originally flat. You are bending this potential energy down, okay? So once you bend it down, this most energetic energy in the metal may have a chance to pass through this barrier and tunnel out, okay? Again, immediately you see, if I apply a stronger field, the bending will be, the line will be even inclined, the barrier will be smaller, okay? So therefore, there is a distance to tunnel through, which is the higher the field, the smaller the distance. Everything makes sense. You apply a stronger field, more electrons can come out. That is field emission, okay? If we apply this tunneling idea through, okay, we will see that there's some prediction about how the field will come in to the current density. This is the charge current density, okay? Electrons times the minus E in front. How will this current density be sensitive to the applied field, okay? There is a W called the work function, that is the barrier still here, the efficiency in energy, okay? So at the end, the formula is something like that, and that is proven experimentally. This is called the Flower-Nordheim tunneling formula. Who is Flower? Flower supervised Dirac's PhD thesis, in which he did the electron Dirac equation theory and also the theory of many electron systems. Okay, that is Flower. Someone, right? Okay, so you know that is tunneling in action. Okay. There's another effect called Richardson effect that is also Nobel Prize winning, but this has to do with thermal energy using KT to thermally excited electron to surpass the barrier. So that is nothing tunneling about it. The next thing I would like to mention just a few minutes more, okay, is our existence. Why we have energy from the sun to support life. So this has to do with our existence. Of course, you know the reason. The reason is fusion, right? Proton, and neutron, basically 4 hydrogen, comes in to become a helium. 2 of them will have to change to a neutron. Okay, so that is fusion, nuclear fusion. But if you think about the fusion process, that is hard to realize, to get it to do fusion for the following reason. So you have a proton in the sun, another proton in the sun. If they are separated, now, in order for them to have nuclear force to come into action to bind them, they need to be close enough femtometer distance so that nuclear force will be strong enough to bind them. Okay, that's the point. However, they are both positively charged. The Coulomb energy is still there, but it's repulsive. So you can imagine, you have 2 protons. How much energy you need in order to force them to close contact to be within femtometer distance, okay? You can easily estimate this. You use this formula, plug in femtometer, you know, you need MeV scale energy. If you change MeV into KT temperature or thermal energy, you know this temperature is 10 to the 10 K. Okay, that is to say, if you can put protons in a hot bath, 10 to the 10 K, even thermally, they could come together to that distance and then they could bind together to form heavier nuclear matter. Okay? If not, how come we have helium so that we can enjoy, well, we have helium in the sun so that we can enjoy the fusion energy from the sun. Okay? That is the question. But there is a problem. We know the sun is not that hot. Okay? On the surface, the sun is something like 5,000, 6,000 K. Even at the center, it is still a few orders of magnitude lower than what we want it to be. Okay? So it's more than thermal. Okay? The sun is not hot enough to use thermal energy to force fusion. So what happened? Again, we have this situation. If we can force them into close enough femtometer range, they will trap. But farther from that, there is a Coulomb barrier to conquer. All right? So the proton now, they are separate. So the proton is outside. Now is the reverse process. Can the proton tunnel through into it to be trapped? Okay? So all the evidence say that the proton does not have sufficient energy to go through the barrier, and therefore tunneling is responsible. And there are standard processes proposed, and I think experimentally verified, that there are energy mechanisms in the sun. One of them is the PP cycle. Here I listed for you. You don't need to know all the details. The issue, the net effect is, at the end, we are putting four hydrogen together to form a nuclear, 4 proton together to form a helium nuclei. In the process, in between, of course, we pick up 2 neutrons, all right? So now, the first process is hard to occur. It is PP into a deuterium and then a positron and a neutrino. Whenever you see something like this as the product, this is a weak interaction process. This is extremely rare and slow, okay? But once this happens, then this 2 other processes could happen. And then we have this process that can give us some energy. This is what we relied on supporting life on Earth, all right? But in physics, we also like this neutrino. These are called solar neutrinos, okay? But this is a separate story. In Diabase, in other experiments, for the past 40 years, 50 years, people have been trying to measure this solar neutrino. Neutrino come from the sun, and the story goes that there is a portion missing. We anticipate there are more, but we only measure maybe half of them. So what happened? So that comes the story about this electron neutrino on the way to Earth can become some other type of neutrino that is called neutrino oscillations. And that is what the group at CUHK headed by Zhu Mingzhong become famous for in the Diabase experiment. But this is the origin of the solar neutrinos, okay? So I mentioned that it burns very slowly because of the first process is slow. But maybe we are enjoying the benefit of weak interaction. And after all, if it burns too quickly, we may be too hot to leave. Okay, so somehow weak interactions start the process. It goes slowly. Just the right amount of sunshine comes in, and we have carbon dioxide trapping some heat in the atmosphere, keeping us warm. So a lot of physics behind our survival. Okay, so on Earth, many experiments nowadays are going on about getting fusion to happen on Earth in a controlled way. Okay, if you don't control it, fine. This is hydrogen bomb. That is easy. I think in the 1950s already bombed. Okay, but if you want to do it in a controlled way, not explosion, then it's still ongoing. The most famous experiment ongoing is this ITER. It's called the International Project of Ignition, something like that. 點火. It is a multinational project. Okay, you can look it up here, and then I think they are going to do it very close to completion. The latest news is as follows. There's another cycle proposed by astrophysicists, especially this very famous one called Hans Bethe. He got the Nobel Prize for proposing that in more massive stars, usually more massive than our sun, there is another path. The net effect, again, is to put 4 protons together to form a helium nucleus. But that needs some carbon to be around. So occasionally, maybe helium feels heavier, you have some carbon, okay? Once you have some carbon around, these processes can do, you add up the left-hand side, right-hand side, it only serves as a catalyst. It will come out again, okay? So all of the things will come out again, okay? So the that effect is still that, okay? And that is easier to occur than the previous PP cycle. So that's Hans Bethe. Hans Bethe was the student of Somerville, a postdoc of Pauli. And he himself has many famous contributions to nuclear physics using quantum mechanics. So the latest situation is that this is a very recent paper in Nature, last year, late November 2020. So here's the abstract. This group, this collaboration, for the first time they claim they have seen the evidence of this particular cycle even occurring in our sun. Okay? And they claim we report direct observation with high statistical significance beyond any sigma, okay? And that this cycle is also occurring in the sun. They observed the neutrino actually. And then the conclusion is that accounts for this carbon, nitrogen, oxygen cycle fusion in the sun to be 1%, okay? The remaining 99% is the previous PP cycle. So this is the latest development in this area, okay? And lastly, just one more page. There are things called resonance tunneling. So if you have this double barrier, the transmission will have sharp peaks, even for energy below U, okay? It can reach 1, ideally, okay? So when you have this, then people can think about it as using it to do switching, okay? Very big is 1, very small is 0, so you can switch from 1 to 0. Okay, so this is a double barrier resonance tunneling. So you can bias two sides, and therefore you can make use of this resonance tunneling to get very strong current only at a particular energy below the barrier. And when you have IV curves that is so drastically changing, you can think about it to be switching devices. The latest, I think that if I'm going to bet, I think Capasso will someday win a Nobel Prize. This is his invention. It is something called quantum cascade laser. So he has this multiple barriers, but he aligned this trapped electronic state in the barrier to be aligned it cleverly so that come in, the electron go down here, tunnel through, then it is in the upper state, come down, emit a photon, tunnel through, come down, tunnel through. Every time when it tunnel through, it is in the higher state of the next well. Okay, so it is rather clever. He already made it for many years. I think it may be of some use already. Okay, other tunneling applications, you can find it in your flash memory, in your tablet nowadays, in your notebook. And then tunneling is also a problem because when people try to make semiconductor device smaller and smaller, then one day they reach the tunneling limit, then everything will be changed. Even some nice thing will be ruined, okay? So tunneling is a limit in some idea about shrinking the circuit to smaller and smaller sizes. And the last page is just some references, okay? So I just want to give you a big picture about just one tiny thing in quantum mechanics. Tunneling could lead to many, many different applications, real life or even out of our control in the sun, that fusion is through tunneling, okay? So that's really ends our course. So I will stop